This image has become the visual backdrop of our civilization. A steel island in the midst of endless blue, a gas flare flickering in the wind, a helicopter coming into land through a storm. We are sold the triumph of engineering, a monumental symbol of human control over nature.
It seems that these structures stand there by right of might, reliable and unshakable in their geometric precision.
But this steel knows how to groan. If you go down to the lower decks, where the waves crash against the support columns, you can feel a low, vibrating rumble. This is not the sound of machinery at work. It is the sound of metal resisting. Behind the flawless images of corporate presentations lies a reality where there is no room for triumph. Only a continuous, exhausting battle of matter against pressure. Micro cracks in the welds, metal fatigue from the cyclic stress of the waves, corrosion eating away millimeters of protection each year, the pressure of compressed gas capable of tearing pipes apart like paper. This structure is neither a building nor a factory. It is a gigantic artificial parasite implanted into the planet's artery.
A complex, vulnerable organism that pumps millions of tons of explosive blood through its metal veins every second.
By the end of this dive, it will become crystal clear why this steel web looks exactly the way it does. You will see that every ton of metal, every valve, and every redundant safety system is not the result of brilliant foresight, but the documented price of past disasters. But to understand the weight of this system, we must go back to the very beginning, to a time when the ocean was simply salt water and economic ambitions had not yet collided with the ruthless physics of the deep. It all began with an attempt to cheat geography. In the swamps of Louisiana and the shallow waters of the Gulf of Mexico, oil lay so close to the surface that it seemed you could reach out and grab it. The ground here was sticky, unstable, consisting of silt and rotting algae. It was a gray zone between land and sea, where the usual laws of construction did not apply. The first oilmen didn't think about global systems or billion-dollar budgets. They thought in terms of ordinary wooden piers. Hundreds of pine piles were driven into the muddy bottom, roughly fastened together with planks and topped with ordinary onshore drilling rigs. It was a dirty, primitive expansion. The wood instantly began to rot from the salt water and was eaten away by marine borers.
Hurricanes, which regularly came from the south, reduced these wooden structures to splinters, scattering the mangled equipment all along the coast.
The system demanded a new material capable of withstanding the strain. Wood was naturally replaced by steel, but the engineering logic remained the same, simply placing a piece of land on iron stilts. Engineers began welding tubular frames, driving them into the seabed at depths of 10 and later 20 meters. This is how the basic design emerged that would become both the bane and the salvation of the industry for decades to come. The steel jacket, a transparent lattice structure made of pipes that absorbed the force of the waves and allowed water to pass through it, minimizing resistance. On these first steel islands, everything was permeated with the smell of crude oil, rust, and sweat. Workers slept in cramped metal trailers right beneath the derrick, deafened by the incessant clanging of drill pipes and the roar of diesel generators. It was a crude compromise between market greed and the engineers' technological helplessness. The platforms were built in sections in sheltered bays and then hauled to the site by shallow draft barges. They were designed for calm waters, warm sun, and a predictable, solid seabed. The illusion of control seemed absolute. Pumps rhythmically lifted the black liquid, underwater pipes stretched toward the shore, bringing in the first super profits. It seemed to man that he had simply extended the coastline, subjugating a few more miles of shallow water without much effort. But the global economy demanded more fuel. Shallow water reservoirs were being depleted faster than new rigs could be built.
Seismic data revealed gigantic hydrocarbon reserves in places where no one in their right mind would attempt to install steel supports.
The industry was forced to venture beyond the edge of the continental shelf, into the open ocean, where there was no protection from headlands, where waves did not break against the seabed, and where storm winds met no obstacles for thousands of miles around. A system designed for warm, shallow waters was preparing to plunge into an environment that was completely unprepared for it. The metal had no idea what physical forces it would face in the coming decades. The steel frame, designed for the short waves of the bay, was about to bear the brunt of thousands of tons of icy water. The era of cheap oil was over, The age of extreme mass was beginning. The North Sea became a testing ground that broke the old rules of the game. This is not the warm, shallow waters of America. It is a giant wind tunnel between Great Britain and Norway. In winter, storms rage here, whipping up 30-meter waves. Walls of water as tall as a 10-story building, carrying the kinetic energy of a freight train. When the massive Ekofisk and Brent fields were discovered here in the late 1960s, oil companies tried to use proven steel frameworks. They simply scaled them up, making the pipes thicker and the supports wider. But the ocean does not forgive linear scaling. The weight of the steel structures grew exponentially, reaching tens of thousands of tons.
To weld these colossal assemblies onshore, factories the size of a small town were required.
And then these mountains of steel had to be transported out to sea. Towing the giant supports took weeks. The metal bent and deformed under its own weight even before it was lowered to the seabed. The battle to secure them began. To prevent the platform from capsizing from the impact of waves, piles were driven 100 meters deep into the seabed. Huge hydraulic hammers pounded for days on end, turning the underwater world into a zone of acoustic terror. But the main problem was the temperature. In the icy waters of the North Sea, the steel behaved differently. It lost its ductility and became brittle. Microscopic welding defects under the influence of cyclic wave impacts turned into fatal cracks. Divers had to descend into the icy darkness to inspect the seams. People worked at the limits of their physiological capabilities, breathing helium mixtures, suffering from decompression sickness, and a cold that penetrated to the bone. The human body became the weakest link in this steel chain. Outwardly, the North Sea platforms looked like impregnable fortresses. They glowed in the polar night with thousands of lights, shooting pillars of flame into the sky. But hidden tension was building up inside that metal. The platforms had outgrown their original function. They had become full-cycle plants in the middle of the sea.
On a single deck were drill pipes, separators for separating gas from oil, chemical storage tanks, and living quarters for hundreds of people.
Everything was compressed into a single, tightly packed cube to save space. Engineers tried to cram the uncrammable. Living quarters were often located directly above gas compressors, separating sleeping people from an explosive mixture by only a few centimeters of steel decking. The system was overloaded with functions. It extracted, purified, pumped, generated electricity, and served as a hotel. And all this under the constant physical pressure of storms from the outside and hundreds of atmospheres of pressure from the wells inside. The complexity of the systems had reached the limits of human control. Kilometers of pipes, thousands of valves, highly sophisticated electronics. And all of this was subjected to constant vibration and salt corrosion. The illusion of durability was sustained only by the incredible efforts of the repair crews. Steel proved too flexible, too malleable for such depths and such loads. A fundamentally different approach to the material was required. The ocean had to be countered not with a lattice, but with absolute, overwhelming mass. The Norwegians solved the North Sea problem with radical Scandinavian directness. If steel bends, rusts, and vibrates, you need to use a material that ignores the waves. They turned to concrete. Thus were born gravity platforms, the heaviest mobile objects ever created by humankind. The concept was frighteningly simple. Create a mass so enormous that the ocean simply couldn't move it. No piles, no anchors to the seabed. The platform was to stand solely on the strength of its own monstrous weight, resting on the seabed with a wide base. The pinnacle of this megalomania was the Trolla platform. It is not just a structure, it is a man-made geological anomaly.
It stands nearly half a kilometre tall and weighs over 1 million tons. It is taller than the Eiffel Tower and heavier than a dozen aircraft carriers.
The construction of these colossal structures defied conventional engineering logic. They could not be built on land. No crane in the world could lift such a weight. They were built directly in the Norwegian fjords, in the sheltered depths of the water. The process was called slip-form construction. Thousands of workers poured high-strength concrete into rising forms continuously, 24 hours a day. 4 giant hollow columns rose directly from the water, millimeter by millimeter. Stopping the process even for an hour risked the collapse of the monolith. The interior of these columns was hollow. They were colossal caissons capable of functioning as ballast tanks. To move the platform out to sea, it first had to be submerged. Water was pumped into the foundation, and 1 million tons of concrete slowly sank beneath the surface, leaving only the top few meters of the columns above water. With the help of a fleet of barges, a steel deck equipped with machinery was carefully lowered onto them. And then the riskiest stage began: towing. A dozen of the most powerful ocean-going tugs on the planet were harnessed to cables as thick as a human leg. They dragged this mountain of concrete across the open sea at a pedestrian's pace.
The slightest navigational error, a sudden storm, and it would have been impossible to save this structure.
When the platform reached its destination, the ballast tanks were filled with water. The concrete colossus slowly and inexorably sank to the seabed. The skirts at its base dug into the seabed, sealing the foundation tightly. The water was pumped out, creating a vacuum that sucked the platform onto the seabed. It was a triumph of statics. Concrete did not rust, did not require painting, did not vibrate under the impact of waves. People inside the columns, descending by elevator to the bottom of the sea, could hear only the muffled, distant sound of water. The illusion of absolute safety had reached its peak. But the concrete giants solved only the external problem, the problem of the storm. The internal threat remained unchanged. All that colossal mass served a single purpose: to keep the steel deck box afloat, packed to the brim with explosive gas under immense pressure. The structure had become immobile, but its internal systems were operating at their limit. The system had survived the waves, but it had created a new vulnerability. The concrete foundation was too expensive, too unwieldy. It was tethered to a single point forever. Dominating the ocean through mass turned out to be an economic dead end. While the concrete giants stood in the north, a technological catastrophe was brewing on other platforms around the world. Compressing functions into a limited space was bound to unleash energy. And that release happened. It rewrote the rules of the game with blood and fire, proving that gravity is not the only force to be reckoned with. By the late 1980s, the industry had come to believe in its invulnerability. Platforms had been operating for decades. Oil flowed in a steady stream, and mechanisms ran like clockwork. But this routine dulled the sense of fear. The system forgot that it was not operating in a factory, but on a powder keg. The Piper Alpha platform became a symbol of this blindness. Originally designed solely for oil production, it gradually took on new functions over time. Modules for gas production and compression were installed on it. The initial streamlined design turned into a chaotic labyrinth of pipes, valves, and compressors. Functional compression had reached a critical mass. There was not enough space. Units that, for safety reasons, should have been located at opposite ends of the structure ended up pressed against one another. The wall of the living quarters, where 200 people slept, was just a few meters from the gas compressor unit. This was not the mistake of a single engineer. It was a systemic disease of cost-cutting. The ocean dictated its own rules. Every square meter of deck space cost millions. Therefore, everything was packed to the limit. The safety system, the control system, and the life support system became entangled in an inseparable tangle. That July night in 1988 revealed the cost of this compression: a chain of minor, almost routine errors, a valve removed for repair, a note not passed on during the shift change, the accidental start of a backup pump, led to a gas condensate leak. A spark in the confined space of the modular grid triggered the first explosion. It was not fatal in itself, but it destroyed the walls of adjacent pipelines. The system began to feed the fire with its own lifeblood. Piper Alpha turned out to be a trap. Firewalls designed for a conventional fire melted like plastic under the jets of burning gas at a pressure of 100 atmospheres. The heat was so intense that the metal of the supporting structures began to flow. People found themselves trapped in the living quarters. Evacuation plans, beautifully drawn up on paper, proved useless. Lifeboats either burned up or failed to detach. Helicopters could not approach due to the heat wave. The disaster was exacerbated by economic integration. Piper Alpha was a hub station where pipelines from other platforms converged, and those platforms continued to pump oil and gas into the epicenter of the fire because managers were afraid to halt production without an order from shore. They fed the fire with millions of dollars, burning people alive. The explosion of the main gas pipeline was the final straw. The massive structure, weighing 30,000 tons, simply collapsed in on itself, crashing into the boiling sea. In 2 hours, a monumental symbol of progress turned into a pool of molten metal and 167 bodies. The crisis showed that the old concept was dead. The cost of the mistake proved too high, not only in lives but also in money. Companies lost billions. The industry needed to be saved through fragmentation. The system had to be split up. People had to be moved away from the compressors. Drilling rigs had to be removed from production platforms. But most importantly, it became clear that the rigid connection to the seabed had become a burden. Oil was being found deeper and deeper. Concrete columns and steel jackets had reached their physical limits. Building a tower to the surface at a depth of 1 kilometer was madness. The structure had to break free from the seabed. To survive and continue their expansion, the steel monsters had to learn to float. The ocean below the 500-meter mark changes its properties. This is a zone of eternal darkness, immense pressure, and unpredictable deep currents. Erecting a rigid structure here means defying the laws of structural mechanics. The steel would collapse under its own weight before reaching the surface. The solution came in the form of the tension leg platform (TLP) concept. Engineers decided to use Archimedes' principle as a force-generating tool. The platform became a giant sealed float whose excess buoyancy pulled it upward toward the sky. But this float had to be held in place. Massive piles were driven into the seabed, to which steel pipes, cables, were attached. The platform was artificially submerged by tensioning these pipes like guitar strings. The colossal buoyancy of the water kept the structure perfectly level. It did not rock on the waves, it stood rigidly, yet without support. This was a new form of fragility. The system's stability depended on the continuous tension of the cables. If even a single cable snapped, the balance was disrupted and the platform could tilt dangerously. Controlling the tension became the operator's new religion. The next step into the depths gave rise to spar-type platforms. These were giant cylinders resembling fishing floats, submerged hundreds of meters underwater. Heavy ballast at the bottom kept the cylinder vertical. Only a small portion of this hidden steel cigar protruded above the surface. Separation from the seabed allowed for the development of incredible depths, 1 kilometer, 2 kilometers. But it complicated the delivery of oil. Previously, pipes ran inside steel supports. Now they had to hang freely in the water from the wellhead to the floating platform. These flexible pipes, risers, became the Achilles heel of deepwater production. They were subjected to currents. They vibrated, wore out, and rubbed against each other. The cold ocean water cooled the oil. Paraffins solidified inside the pipes, clogging them like blood clots in arteries. We had to wrap the risers in layers of insulation and install heating systems. The infrastructure grew more complex with every meter of depth. The system ceased to be a rigid structure. It became a dynamic network, constantly balancing in the water column. But the biggest challenge was not the platforms, but the ships. FPSOs, floating production and storage and offloading, are floating refineries. These are supertankers with a full-scale oil refining complex mounted on their decks. They are tethered to nothing but anchors and a flexible hose running to the seabed. They rotate around this hose like weather vanes, presenting the narrowest bow profile to the storm. If a hurricane strikes, they can disconnect the hose and sail away. An illusion of mobility and safety. But this mobility required the installation of turrets, extremely complex rotating mechanisms inside the ship's hull, through which dozens of pipes carrying oil and gas pass under immense pressure. A single failure in the turret seals, and the ship is flooded with an explosive mixture. The structure survived by breaking free from the seabed, but lost its original monumental simplicity. It turned into a highly complex mechanical ballet, where dozens of dynamic systems must work in sync. Cables, anchors, flexible pipes, dynamic positioning systems. The burden shifted from metal to electronics. Computers now monitored every inch of deviation from the drilling point. The human on board became merely an observer of the algorithms. But algorithms cannot foresee the depths. When the drill penetrates 3 kilometers below the water's surface and then another 5 kilometers into the rock, the physics of pressure returns with double the force, and electronics prove powerless against the primal energy of the Earth. Deepwater drilling is like performing surgery blindfolded. A tool several kilometers long is lowered into the darkness, piercing through layers of salt and hard rock to reach a reservoir under hundreds of atmospheres of pressure. The entire system balances on a single thin line, a column of drilling mud, the slurry pumped into the well. The weight of this column must precisely counterbalance the pressure from the Earth's depths, preventing oil and gas from escaping to the surface. It is a fragile equilibrium dependent on calculations of the mud's density. By April 2010, the industry believed it had tamed the abyss. Semi-submersible drilling rigs, such as Deepwater Horizon, were considered the pinnacle of evolution. They were held in place solely by GPS and giant propellers, hovering over the drilling site a kilometer from the seafloor. But the complexity of the rescue created a new vulnerability. The drilling process had become so expensive that time became the main enemy. Companies were in a hurry. Mistakes in choosing the cement to seal the well, ignoring the results of pressure tests, all of this was driven by the desire to finish the job faster and move the platform to a new location. Control of the energy shifted to a single device at the bottom of the ocean, the blowout preventer, BOP. This is a multi-ton steel block of valves, the last line of defense. If gas breaks through the cement, the BOP must use hydraulic blades to cut through the drill pipe and seal the well shut. But mechanisms that aren't properly maintained break down. When methane under colossal pressure breached the defective cement plug and surged up the pipe, the blowout preventer failed. The blades couldn't cut through the steel. The last safety mechanism failed. The methane reached the platform, expanding as the water pressure dropped. Within minutes, an invisible cloud of gas enveloped the deck, entered the ventilation system, and reached the running diesel generators. The same thing happened as on Piper Alpha, but this time in the open ocean on a floating structure. The explosion destroyed the power and control systems. The massive floating city burst into flames like a match. 2 days later, the burnt-out hull of the Deepwater Horizon sank to the bottom, severing the connecting pipes. And that's when the true cost of deepwater drilling became clear. In shallow water, the well could have been plugged by divers or controlled explosions. But at a depth of 1,500 meters, humans are powerless. The water pressure would crush any flesh. Oil gushed from the open wound at the bottom of the ocean. For 87 days, the whole world watched live as technology proved helpless. ROVs with mechanical manipulators tried in vain to close the broken preventer valves. It looked like an attempt to repair a Swiss watch with a sledgehammer in complete darkness. The solution required drilling new relief wells. Months of work, billions of dollars in fines, dead ecosystems, and legislation changed forever. The disaster proved that when a system operates at extreme depths, an accident cannot be quickly contained locally. The cost of a mistake becomes global. The ocean has become too hostile an environment for human presence in the production zone. The illusion of safe manual control has vanished. The industry realized that people must be removed not only from the compressors, but also from the water's surface itself. The final, most terrifying transformation has begun. The facility was preparing to disappear from view. Today, the architecture of oil control is sinking to the bottom. The era of giant steel islands and concrete leviathans piercing the ocean's surface is slowly coming to an end. The surface is too unstable. There are hurricanes, waves, icebergs, and, most importantly, the human factor. A true technological revolution is taking place in complete darkness, 3 kilometers below the surface. The concept of the subsea factory, underwater plants, is emerging. These are no longer just valves and pipes. They are giant compressor stations, separators, and pumps mounted directly on the ocean floor. They are powered by cables from the shore or from small floating buoys. They don't need oxygen. They don't need mess halls, lifeboats, or helipads. They aren't bothered by the wind because eternal calm reigns at that depth. The ocean has transformed from an enemy into the perfect cooling system for overheating machinery. These steel modules, the size of a high-rise building, are lowered to the sea floor by cranes. Pipe connections are made without human intervention. ROVs, controlled by operators thousands of kilometers away, carefully tighten valves and connect cables. The extraction process has become fully automated, silent, and invisible. Oil and gas are pumped from the Earth's depths, separated into fractions right on the seabed, and forced under pressure through pipes straight to onshore plants. But this new form of invisibility carries with it a new absolute fragility. Equipment operating in aggressive salt water under hundreds of bars of pressure requires perfect sealing. Replacing a tiny seal, which takes 10 minutes on land, turns into a multi-million-dollar special operation at the bottom of the sea, involving specialized vessels. Electric cables stretching hundreds of kilometers along the seafloor are vulnerable to underwater landslides and even stray anchors. If the system at the bottom fails, it does so silently. You won't see smoke or hear an explosion. The pressure in the riser will simply drop to zero. We have moved the infrastructure into an environment that we control only through monitor screens. The object of extraction is no longer a building, a platform, or a ship. It has become a distributed cybernetic network whose neurons are fiber optic cables and whose synapses are robotic valves at the bottom of the abyss. Humans have been definitively banished from this habitat. They created instruments of power that no longer require their physical presence to keep the economy's pulse beating. Machines worth billions of dollars operate in the icy darkness, silently pumping the black blood of the earth. This is the pinnacle of engineering thought, brought to a sterile absolute. The system survived only by completely abandoning the form with which it began its journey. The wooden pilings of the Louisiana swamps have evolved into autonomous titanium blocks of the abyss. Look again at that image at the beginning of the journey. At the gleaming platform defying the storm, you no longer see just steel and concrete. You see the multi-layered scar of evolution. You see compromises whitewashed and fears encased in titanium. In 100 years, we have not conquered the ocean. We have simply learned to make our tools heavy, buoyant, or invisible enough that the water does not destroy them instantly. The price of these machines is not measured in billions of dollars of investment. Their true price is the accumulated weight of disasters, the fatigue of overburdened materials, and the forced isolation of entire systems at the bottom. Every modern nut in these factories is tightened with past collapses and explosions in mind. We have created a global circulatory system of metal to sustain our familiar world of consumption. And this system demands constant expansion into the darkest, most hostile corners of the planet, because stopping means collapse. They stand there right now, hidden beneath the water or towering above it, vibrating from internal pressure, battling corrosion and the cold. Instruments of power that have long outgrown their creators in scale and complexity. The machines are running, the ocean waits, the balance is maintained until the next breakdown.